Around 359 million years ago, Earth entered the Carboniferous Period, a time of major environmental and biological change. During this period, vast forests spread across much of the land. Giant insects became common, and many amphibians lived in large swamps and rivers. Plants removed large amounts of carbon dioxide from the atmosphere, and over millions of years, their remains formed many of the coal deposits that are mined today. New groups of plants and animals continued to evolve, while the earliest reptiles became more widespread. The Carboniferous Period played an important role in shaping Earth's climate, ecosystems, and the future development of life. The Carboniferous Period began about 359 million years ago and ended about 299 million years ago. It was one of the major periods in Earth's long history and formed an important part of the Paleozoic era. During this long span of time, the planet experienced many important changes that affected the land, the seas, the climate, the atmosphere, and the living things that inhabited Earth. Scientists study this period because it contains many clues about how the natural world changed over millions of years. Rocks, fossils, ancient soils, and other remains from this period help researchers understand the conditions that existed at that time. The name Carboniferous comes from the Latin word for coal. This name was chosen because many of the world's largest coal deposits were formed during this period. Thick layers of dead plants collected in large wetlands and swamps over very long periods of time. As these plant remains were buried under mud, sand, and other materials, heat and pressure slowly changed them into coal. These coal deposits later became an important source of energy for human societies many millions of years after the Carboniferous Period had ended. The Carboniferous Period followed the Devonian Period and came before the Permian Period. Each of these periods had its own conditions and living things, but the Carboniferous is especially well known for its rich plant life, its large forests, and the great variety of animals that lived on land and in the oceans. It was a time when many forms of life spread into new environments and developed new ways of surviving. At the beginning of the Carboniferous Period, Earth already supported a wide variety of living things. Plants covered many areas of land, insects had become common, and different groups of fish filled rivers, lakes, and oceans. Early amphibians had also appeared during the Devonian Period, and many of them continued to develop during the Carboniferous. Over time, new groups of animals appeared and spread across different parts of the world. The Carboniferous Period lasted for about 60 million years. This long stretch of time allowed many slow natural processes to take place. Mountains slowly rose as continents moved. Rivers changed their paths across the land. Coastlines moved as sea levels rose and fell. Forests expanded into new areas where the climate allowed plants to grow. Living things slowly changed through evolution as each generation passed on its characteristics to the next. During much of the Carboniferous Period, the climate was warm and moist in many regions. Large amounts of rainfall supported the growth of thick forests filled with giant club mosses, horsetails, ferns, seed ferns, and early trees. These forests covered huge areas, especially near the equator. Wet conditions allowed plants to grow quickly and produce large amounts of plant material. Dead plants often fell into swampy ground, where there was little oxygen. Because the plant remains did not fully decay, they slowly built up into thick layers that later became coal. The continents during the Carboniferous Period were arranged very differently from the way they are today. The land that now forms North America and Europe lay much closer together than they do in the present day. Many southern continents were joined together as part of a giant landmass called Gondwana. Other northern land areas formed another large landmass known as Euramerica. Over millions of years, these continents slowly moved closer together through the movement of Earth's tectonic plates. Their movement eventually helped create the supercontinent known as Pangaea. The movement of continents affected the climate, the oceans, and the shape of the land. When continents collided, they formed long mountain ranges. These mountains changed weather patterns and influenced the flow of rivers. As land rose higher, erosion carried rocks and soil into nearby basins, where thick layers of sediment slowly collected. These sediments later hardened into rocks that geologists study today. Sea levels changed many times during the Carboniferous period. At some times, shallow seas spread across large parts of the continents. At other times, sea levels dropped, exposing more land. These repeated changes created many different environments where different kinds of plants and animals could live. Marine animals flourished in shallow seas, while forests and wetlands expanded across exposed land. The oceans of the Carboniferous were rich with life. Coral reefs supported many different animals: brachiopods, crinoids, bryozoans, mollusks, trilobites, ammonoids, and many kinds of fish lived in marine environments. Sharks also became more common and developed into many different forms. Some fish had strong jaws for catching prey, while others fed on smaller organisms living in the water. Freshwater environments such as rivers, lakes, and swamps also supported many living things. Fish filled these waters, while amphibians hunted along the edges. Many insects lived among the plants growing near the water. These habitats provided food, shelter, and places where animals could reproduce. Plants reached remarkable levels of growth during the Carboniferous period. Some club mosses grew to the height of modern trees. Giant horsetails and seed ferns formed dense forests. Ferns spread across moist ground, creating thick layers of vegetation beneath the taller plants. These forests looked very different from modern forests, because flowering plants had not yet evolved. There were no grasses, flowering shrubs, or flowering trees. Instead, the landscape was dominated by spore-producing plants and early seed-bearing plants. Plant reproduction during this time depended on different methods. Many plants produced spores, which were carried by the wind or water to new places where they could grow. Other plants had begun producing seeds. Seeds provided better protection for young plants and helped them survive in changing conditions. The development of seeds became one of the most important steps in the history of plant evolution. The atmosphere during the Carboniferous period contained higher levels of oxygen than today. Scientists believe this increase happened because large forests produced enormous amounts of oxygen through photosynthesis. At the same time, large amounts of carbon became trapped inside buried plant material instead of returning to the atmosphere. Higher oxygen levels may have helped some insects grow much larger than similar insects living today. Some insects during the Carboniferous reached sizes rarely seen in later periods. Giant dragonfly relatives flew above forests and wetlands. Large millipedes crawled across the forest floor. Many other insects developed wings, allowing them to travel more easily in search of food and mates. Flying insects became an important part of many ecosystems. Amphibians became one of the dominant groups of land animals during the Carboniferous period. These animals usually depended on water for reproduction because their eggs needed moist conditions. They lived near rivers, lakes, swamps, and wetlands where water was always available. Some amphibians became large predators that hunted fish, insects, and smaller animals. Others remained smaller and fed on insects or other tiny creatures. One of the most important developments during the Carboniferous period was the appearance and spread of the earliest true reptiles. Unlike amphibians, reptiles produced eggs with protective coverings that could survive on land. This allowed them to reproduce farther away from water. Their skin also reduced water loss, helping them live in drier environments. These changes opened new opportunities for animals to spread into different habitats. The evolution of reptiles marked an important step in the history of life on Earth. Over many millions of years, reptiles would give rise to many different groups of animals, including dinosaurs, birds, and mammals through separate evolutionary paths. During the Carboniferous itself, however, reptiles remained relatively small compared to many later forms. Life in the Carboniferous forests involved countless interactions between plants, insects, amphibians, reptiles, fungi, and tiny organisms living in the soil. Plants captured energy from sunlight and formed the base of food chains. Plant-eating animals fed on leaves, stems, spores, and seeds. Predators hunted smaller animals, while fungi and bacteria helped break down dead material. These relationships created balanced ecosystems that changed slowly over time. Fungi played an important role in Carboniferous environments. They helped break down dead plants and recycled nutrients back into the soil. Without fungi and other decomposers, dead plant material would have built up even more rapidly than it already did. Different kinds of fungi work together with bacteria and other microorganisms to support healthy forest ecosystems. The Carboniferous period is divided into two parts by many geologists. In North America, these are called the Mississippian and the Pennsylvanian. In other parts of the world, scientists often use different international stage names to describe the same period in greater detail. These divisions help researchers organize rock layers and understand the sequence of events preserved in the geological record. The rocks formed during the Carboniferous period are found on every continent. These rocks include limestone, sandstone, shale, coal, and many other types. Each kind of rock formed under different environmental conditions. Limestone often formed in shallow seas, where marine organisms produced shells and skeletons. Sandstone formed from sand deposited by rivers, beaches, or deserts. Shale developed from fine mud settling in quiet waters. Coal formed from buried plant material in ancient wetlands. Fossils preserved within these rocks provide valuable information about ancient life. Fossils include bones, teeth, shells, leaves, spores, footprints, burrows, and even fossilized droppings. Each fossil gives scientists clues about the animals and plants that lived long ago, how they behaved, what they ate, and the environments in which they lived. Scientists use many different methods to study the Carboniferous period. Geologists examine rock layers to understand ancient environments. Paleontologists study fossils to learn about extinct organisms. Chemists analyze the chemical composition of rocks and fossils. Climate scientists investigate ancient temperatures and rainfall patterns. Each field contributes valuable information that helps build a clearer picture of Earth's distant past. Modern technology has greatly improved the study of Carboniferous rocks and fossils. Powerful microscopes allow researchers to examine tiny fossil spores and pollen grains. Medical scanning equipment helps scientists study fossils without damaging them. Computer models allow researchers to test ideas about ancient climates, ocean circulation, and continental movement. Satellites help locate geological formations that may contain important Carboniferous rocks. The Carboniferous atmosphere differed from today's atmosphere in several ways. Higher oxygen levels supported active animal life, while carbon dioxide levels gradually changed over time. The balance between these gases influenced temperatures, plant growth, and the overall climate. Scientists continue studying these changes to understand how Earth's atmosphere has developed through geological history. Climate conditions during the Carboniferous were not the same everywhere. Regions near the equator remained warm and wet for much of the period, supporting extensive forests and swamps. Scientists continue studying these changes to understand how Earth's atmosphere has developed through geological history. Climate conditions during the Carboniferous were not the same everywhere. Regions near the equator remained warm and wet for much of the period, supporting extensive forests and swamps. Areas farther from the equator experienced different seasonal patterns and temperatures. Toward the later part of the Carboniferous, large ice sheets developed across parts of Gondwana. This marked one of the major ice ages of the Paleozoic era. The growth of glaciers affected sea levels around the world. When more water became locked inside ice sheets, sea levels fell. When glaciers melted, sea levels rose again. These repeated changes influenced coastlines, river systems, and marine habitats. They also affected where forests could grow and where coal-forming swamps developed. Earth's interior continued to shape the surface throughout the Carboniferous period. Heat deep inside the planet drove the movement of tectonic plates. Earthquakes, volcanic activity, mountain building, and continental movement slowly changed landscapes over millions of years. These geological forces continue operating today, although the arrangement of continents has changed greatly since the Carboniferous. Many mountain ranges seen today began forming during this period as continents collided. These collisions compressed rocks, folded layers of sediment, and pushed land upward. Erosion gradually wore down these mountains, carrying sediments into nearby valleys and shallow seas. Those sediments later became part of the geological record preserved in Carboniferous rocks. Coal formed during the Carboniferous became extremely important to human history millions of years later. During the Industrial Revolution, coal provided fuel for factories, steam engines, ships, railways, and homes. It helped produce electricity and supported the growth of modern industries. The Carboniferous period is divided into two main parts. These two parts are called the Mississippian epoch and the Pennsylvanian epoch. Each of these epochs had its own environmental conditions, living organisms, and geological events. Although they belong to the same Carboniferous period, they show important differences in the history of the Earth. Dividing the Carboniferous into these two epochs helps scientists understand how the world changed step by step over a long stretch of time. The names Mississippian and Pennsylvanian were first used by geologists who studied rock layers in North America. They noticed that certain rock formations found in one area were different from those found in another area. These differences showed that the Carboniferous period included two distinct stages of geological history. Over time, these names became widely accepted, especially in North America. In many other parts of the world, scientists often use different names based on international geological divisions, but the idea of separating the Carboniferous into an earlier and a later part remains the same. The Mississippian epoch came first. It began at the start of the Carboniferous period and continued for many millions of years. During this time, much of the Earth had warm conditions, although temperatures and rainfall varied from place to place. Many regions were covered by shallow seas. These seas spread across large parts of the continents and supported many kinds of marine life. Thick layers of limestone formed in many places because of the remains of sea animals and the chemical processes taking place in the water. These limestone rocks are among the most important signs of the Mississippian epoch. The name Mississippian comes from the Mississippi River Valley in the United States, where many thick limestone rock layers from this time were first carefully studied. Geologists found that these rocks contained many fossils of sea animals. These fossils allowed scientists to identify the age of the rocks and understand the environments in which they formed. Similar rocks have since been found in many other parts of the world, showing that shallow seas were common during much of the early Carboniferous. During the Mississippian epoch, sea levels were generally high. Water covered many low-lying areas of the continents. These shallow inland seas were rich in life. Many kinds of animals lived on the sea floor, swam through the water, or floated near the surface. The seas contained many crinoids, brachiopods, corals, bryozoans, mollusks, trilobites, and different kinds of fish. Some of these groups had already existed for millions of years before the Carboniferous, while others continued to become more diverse during this epoch. Crinoids were especially common during the Mississippian epoch. These marine animals lived attached to the seafloor by long stems. They used their feather-like arms to collect tiny food particles from the water. Large numbers of crinoids lived together in some shallow seas. When they died, their hard skeletal parts settled on the seafloor. Over very long periods, these remains became part of thick limestone deposits. Many Mississippian limestones contain countless pieces of crinoid skeletons. Brachiopods were another important group during this time. These animals had two shells and lived on the sea floor. Although they looked somewhat like clams, they belonged to a different group of animals. Many different species of brachiopods lived in the warm, shallow seas of the Mississippian epoch. Their fossils are common in Carboniferous rocks around the world. Corals also formed important communities. Some species lived alone, while others formed colonies. Coral communities provided homes for many smaller sea animals. Their hard skeletons became part of the limestone deposits that formed in shallow marine environments. Bryozoans were small colonial animals that built branching or net-like structures made from calcium carbonate. They lived in large groups attached to hard surfaces beneath the sea. Their remains are also found in many Mississippian rock layers. Fish continued to become more diverse during the Mississippian epoch. Sharks were becoming increasingly successful. Many kinds of bony fish also lived in rivers, lakes, coastal waters, and shallow seas. Some fish had powerful jaws and large teeth that allowed them to feed on other animals. Others fed on smaller creatures or plants. Fish occupied many different environments and became an important part of aquatic ecosystems. Life on land also continued to develop during the Mississippian epoch. Forests expanded across many regions where conditions were warm and wet. Large club mosses, horsetails, seed ferns, and true ferns became common parts of these forests. These plants grew in swampy lowlands as well as in other moist environments. Their remains later became buried beneath layers of mud and sand. Over immense periods of time, heat and pressure transformed much of this plant material into coal. Although coal formation began during the Mississippian epoch in some places, the greatest coal-producing environments developed later during the Pennsylvanian epoch. Even so, many early swamp forests had already become well established during the Mississippian. These forests provided food and shelter for a growing variety of land animals. Early amphibians continued to spread during the Mississippian epoch. These animals had evolved from earlier fish ancestors during the Devonian period. They still depended heavily on water for reproduction because their eggs usually needed moist environments. Many amphibians lived near rivers, lakes, ponds, marshes, and swamps. Some spent much of their lives in water, while others could move across land for longer periods. The atmosphere during much of the Mississippian epoch contained increasing amounts of oxygen. Large forests absorbed carbon dioxide and stored carbon in their tissues. When many of these plants became buried before they completely decayed, carbon remained trapped underground. This process helped change the balance of gases in the atmosphere over long periods. High oxygen levels supported many forms of animal life. The continents continued to move slowly during the Mississippian epoch because of plate tectonics. Large landmasses gradually approached one another. These movements caused mountain-building events in several regions. As continents collided, layers of rock folded and rose to form mountain ranges. These geological changes influenced rivers, coastlines, rainfall, and local climates. Sediments carried by rivers entered shallow seas and accumulated layer upon layer. Sand, mud, and shells slowly hardened into sedimentary rocks. These rocks preserve important evidence about ancient environments. Scientists study these rock layers to understand changing sea levels, climates, and ecosystems throughout the Mississippian epoch. Toward the later part of the Mississippian epoch, environmental conditions began to change in many places. Sea levels did not remain constant. Some shallow seas slowly retreated as land became exposed. In other regions, water continued to cover broad areas. These changes affected the types of plants and animals living in different environments. The transition from the Mississippian epoch to the Pennsylvanian epoch did not happen suddenly across the entire world. Instead, it was a gradual process that unfolded over long periods. Some regions experienced environmental changes earlier than others. Scientists identify the boundary between the two epochs by studying fossils, rock layers, and changes in geological conditions. The Pennsylvanian epoch followed the Mississippian epoch and formed the later part of the Carboniferous Period. It is named after the state of Pennsylvania in the United States, where extensive coal-bearing rock formations were first studied in great detail. These rocks showed that conditions during the later Carboniferous differed in important ways from those of the earlier Carboniferous. One of the most famous features of the Pennsylvanian epoch was the widespread development of coal-forming swamps. Warm temperatures, abundant rainfall in many regions, and extensive lowland wetlands allowed enormous amounts of plant material to accumulate. Dead plants often fell into waterlogged ground, where decay was slow because little oxygen reached the buried material. Layer after layer of plant remains accumulated beneath mud and sediment. Over millions of years, pressure and heat transformed these buried plants into thick coal beds. Coal deposits formed during the Pennsylvanian epoch are found in many parts of the world. They became one of the most valuable natural resources for human societies much later in history. These coal beds provided fuel for homes, factories, railways, ships, and electricity generation during the Industrial Revolution and beyond. The formation of these coal deposits began with the ancient forests that covered much of the Carboniferous landscape. The forests of the Pennsylvanian epoch were rich in plant diversity. Giant club mosses reached impressive heights. Horsetails grew in dense stands near rivers and wetlands. Seed ferns spread widely across many swamp forests. True ferns covered the forest floor and moist areas beneath taller plants. Early seed-producing plants became increasingly important because they reproduced without depending entirely on standing water. The spread of seed plants marked an important stage in plant evolution. Seeds protected young plants during development and allowed reproduction under a wider range of environmental conditions. Although many seed plants still preferred moist habitats, they gradually became capable of growing in places where earlier, spore-producing plants found survival more difficult. During the Pennsylvanian epoch, oxygen levels in the atmosphere reached very high values. These high oxygen concentrations influenced many forms of life. Insects became especially successful. Some species reached much larger sizes than most insects living today. Dragonfly relatives developed broad wings and became active hunters. Giant millipedes moved across the forest floor while feeding on decaying plant material. Large relatives of modern cockroaches were also common. The high oxygen content supported active animal life, although body size also depended on many other biological and environmental factors. Not every insect became enormous, and different groups responded differently to changing conditions. Even so, the Pennsylvanian forests supported some of the largest land arthropods known from Earth's history. Amphibians also became more diverse during the Pennsylvanian epoch. Many species lived in swamps, rivers, lakes, and wetlands. Different forms adapted to different ways of feeding and living. Some hunted fish and aquatic animals, while others captured insects or smaller land animals. Amphibians occupied many ecological roles within Carboniferous ecosystems. One of the most important developments during the Pennsylvanian epoch was the appearance and spread of early reptiles. These animals evolved from amphibian ancestors but developed eggs, protected by shells and internal membranes. These eggs allowed reproduction away from open water because they protected the developing young from drying out. This important adaptation allowed reptiles to expand into drier environments that were less suitable for many amphibians. The rise of reptiles marked a major change in the history of life on land. Early reptiles were generally small, but they represented a new evolutionary path. Over the following geological periods, reptiles would diversify into many different forms and eventually include dinosaurs, pterosaurs, marine reptiles, turtles, crocodilians, snakes, lizards, birds, and many extinct groups. Climate during the Pennsylvanian epoch became more variable than during much of the earlier Carboniferous. In the southern part of the supercontinent Gondwana, large ice sheets expanded across extensive areas. These glaciers caused repeated changes in global sea levels. As glaciers grew, more water became stored as ice, causing sea levels to fall. When glaciers melted, sea levels rose again. These repeated rises and falls of sea level affected coastlines around the world. Shallow seas advanced over land during some intervals and retreated during others. Swamps expanded during certain periods and disappeared during others. Rivers changed their courses and new sediment layers covered older landscapes. These repeated environmental shifts produced alternating layers of sandstone, shale, limestone, coal and other rocks that geologists still study today. The movement of continents continued throughout the Pennsylvanian epoch. The gradual collision between major continental masses continued to build mountains. These mountain-building events affected weather patterns, erosion, river systems, and sediment transport. Rivers carried enormous amounts of sediment from newly formed mountains into nearby basins, where thick rock layers accumulated. The assembly of the supercontinent Pangaea progressed during the Pennsylvanian epoch. Continents that had once been separated slowly moved together over millions of years. This process reduced the number of wide oceans separating the continents and created one enormous landmass surrounded by a global ocean. The formation of Pangaea influenced climates across much of the Earth by changing wind patterns, rainfall, and ocean circulation. Scientists distinguish the Mississippian and Pennsylvanian epochs using many kinds of evidence. Fossils provide one of the most important tools. Certain species appeared only during the Mississippian, while others became common mainly during the Pennsylvanian. When geologists discover these fossils in rock layers, they can often determine the relative age of the rocks. Rock types also help distinguish the two epochs. thick marine limestone deposits are especially common in many Mississippian sequences because shallow seas covered broad areas. Pennsylvanian rocks often contain repeated layers of coal, shale, sandstone and limestone produced by changing sea levels and expanding swamp environments. Although both epochs include many different rock types, their overall patterns often differ. Scientists also study microscopic fossils such as spores, pollen grains, and tiny marine organisms. These microscopic remains preserve important evidence about ancient environments and plant communities. They help geologists match rock layers found in different countries and continents. Radiometric dating provides another important method for understanding the ages of Carboniferous rocks. Certain minerals contain radioactive elements that slowly change into other elements at predictable rates. By measuring these changes, scientists estimate the ages of rocks and compare geological events across different regions of the world. The Mississippian and Pennsylvanian epochs are recognized differently in different geological traditions. In North America, these names remain widely used because they fit the local rock record very well. In international geological classification, the Carboniferous period is divided into several smaller stages grouped within lower and upper subdivisions. Even so, many scientists continue using the traditional North American names because they remain useful for describing broad patterns in Carboniferous history. The geography of the Carboniferous world was very different from the geography of Earth today. During this long period of Earth's history, the continents were not located where they are now. They were slowly moving because of the movement of large pieces of Earth's outer shell, known as tectonic plates. This movement happened very slowly over millions of years, but it constantly changed the shape of the planet. Oceans opened and closed, mountains rose, coastlines changed, rivers formed new paths, and large areas of land were covered by shallow seas. The Carboniferous world was shaped by all of these changes, creating an environment that supported many forms of life on land and in the sea. The Carboniferous period began about 359 million years ago and ended about 299 million years ago. During this time, Earth experienced many important geographical changes. Some continents slowly moved toward one another, while others became separated by wide oceans. The movement of the continents affected weather patterns, sea levels, plant life, animal life, and the formation of rocks that can still be studied today. One of the most important geographical features of the Carboniferous world was the gradual formation of a giant landmass that would later become known as the supercontinent, called. During the early part of the Carboniferous period, this huge landmass had not yet fully formed. Several large continents were still separate, although they were slowly moving closer together. As millions of years passed, these continents continued to move until they became joined over a very large area. This process changed the geography of nearly every part of Earth. One of the largest continents during the Carboniferous period was Mambambo. Gondwana covered much of the southern hemisphere and included land that would later become modern South America, Africa, Antarctica, Australia, the Indian subcontinent, and the Arabian Peninsula. Although these places are now separated by wide oceans, they were once connected as one enormous landmass. Gondwana stretched across a very large area and had many different environments because of its great size. The southern parts of Gondwana reached close to the South Pole. Because of this location, large areas experienced very cold conditions. Thick sheets of ice covered parts of the continent during several parts of the Carboniferous period. These glaciers slowly moved across the land, scraping rocks, carrying broken pieces of stone, and leaving behind many marks that scientists can still find today. The presence of these ancient glaciers shows that not every part of Earth was warm during the Carboniferous period. Farther north, conditions became warmer. Some parts of Gondwana received large amounts of rain and supported forests filled with ancient plants. Rivers flowed across wide plains, carrying mud, sand and other materials into lakes and shallow seas. Over long periods of time, these materials formed thick layers of sediment that later became sedimentary rocks. Another major continent during the Carboniferous period was Snarts, which is also sometimes called Euramerica. This continent was formed earlier when smaller landmasses joined together. Laurussia included areas that would later become much of North America, Greenland, parts of Europe, and nearby regions. During the Carboniferous period, much of Laurussia was located near the equator. This position gave many regions a warm and wet climate that was suitable for the growth of large forests. The equatorial regions of Laurussia became home to huge swamp forests. The land was often flat and water collected across broad areas. Rivers frequently overflowed their banks, leaving behind fresh layers of mud. Plants grew in great numbers because the warm temperatures and heavy rainfall provided excellent conditions for growth. Dead plant material collected in the waterlogged ground, where it broke down very slowly because there was little oxygen in the wet soil. Over millions of years, this material was buried under more sediment and slowly changed into coal. The formation of these coal deposits became one of the most important geographical events of the Carboniferous period. Thick coal layers formed in many places that are now found in North America, Europe, and Asia. Today, these coal deposits provide valuable evidence about the geography, climate, and plant life of the Carboniferous world. Another important continent during this time was this landmass was separate from Laurussia and Gondwana for much of the Carboniferous period. It lay farther north and had different climates across its wide area. Some parts experienced cooler conditions, while others had environments that changed as the continent slowly moved. The continent known as also existed during the Carboniferous period. It was made up of smaller pieces of land that had joined together over time. As tectonic plates continued to move, Kazakhstania slowly approached neighboring continents. This movement later helped create new mountain ranges through the collision of continental crust. Many smaller islands and pieces of continental crust were scattered across the oceans. These land areas slowly moved because they rested on tectonic plates. Some eventually collided with larger continents, while others became attached after millions of years of movement. These collisions caused strong pressure within Earth's crust. Rocks were folded, broken, and pushed upward, creating new mountains. Mountain building was an important part of Carboniferous geography. Several major mountain ranges began to form or continued growing during this period. As continents collided, enormous forces pushed rocks upward over long periods of time. The mountains created by these collisions were much taller when they first formed than many of their remains are today. Millions of years of weathering and erosion later wore them down. One important mountain building event was the formation of This happened as Gondwana slowly approached Laurussia. The pressure from the collision helped create mountains in areas that are now part of eastern North America. These mountains were connected with mountain systems that also extended into parts of Europe before the continents later separated. Another important mountain building event was the Eye, also known in some places as the Hercynian orogeny. This event affected large parts of Europe as different pieces of continental crust collided. Huge forces folded layers of rock and raised mountain ranges across wide regions. Many rocks found in Europe today preserve evidence of these ancient geological events. The Carboniferous world also contained many shallow inland seas. Sea levels changed many times throughout the period. Sometimes the oceans spread over low-lying land, creating shallow seas that covered broad regions. At other times, sea levels dropped, exposing large areas of land. These repeated changes greatly influenced where plants and animals could live. The shallow seas were rich in marine life. Warm water allowed many different kinds of animals to thrive. Coral communities, shellfish, crinoids, brachiopods, sharks, and many other sea creatures lived on or near the sea floor. Their remains later became buried beneath layers of sediment, eventually forming fossil-rich rocks that scientists study today. The coastlines of the Carboniferous world looked very different from modern coastlines. As sea levels rose and fell, shorelines constantly changed. New beaches formed while older ones disappeared beneath the sea. River mouths shifted as rivers changed direction or built new deltas. Coastal swamps expanded and shrank depending on rainfall, sea level, and the amount of sediment carried by rivers. Large river systems crossed many parts of the continents. These rivers carried water from mountains into lowland plains and shallow seas. They transported enormous amounts of sand, mud, gravel, and dissolved minerals. During floods, rivers spread these materials across wide floodplains. Each flood added another layer of sediment that slowly built thick deposits over time. Floodplains became some of the richest environments for plant growth. The regular arrival of fresh sediment added nutrients to the soil. Standing water remained in many places throughout the year, allowing swamp forests to continue growing. Fallen trees, leaves, roots, and other plant material accumulated in these wet environments. Many lakes also existed throughout the Carboniferous world. Some formed where rivers changed course. Others developed in low areas where water collected. Lakes supported fish, amphibians, insects, and many smaller forms of life. Sediments settled to the bottom of these lakes, preserving fossils that provide important information about ancient ecosystems. The oceans themselves were arranged differently from today. One of the largest oceans during the Carboniferous period was This enormous ocean surrounded much of the world's land. It covered a huge part of Earth's surface and connected many different marine environments. Another important body of water was This ocean separated several continents and played an important role in marine life and continental movement. As tectonic plates shifted, the size and shape of this ocean gradually changed. The geography of the Carboniferous world strongly influenced climate. Areas near the equator usually experienced warm temperatures and abundant rainfall. Regions near the poles were much colder and supported glaciers during parts of the period. Between these extremes were areas with changing seasonal conditions. Rainfall was not evenly distributed across the continents. Some regions received heavy rain throughout much of the year, while others became drier, as mountains blocked moisture carried by winds. The arrangement of continents influenced the direction of winds and ocean currents, which affected regional climates. The presence of extensive forests also influenced local environments. Trees released water into the air through their leaves, helping maintain high humidity in many regions. Thick vegetation protected soils from erosion in some places, while rivers removed soil from other areas during floods. Volcanic activity occurred in various regions throughout the Carboniferous period. Volcanoes formed where tectonic plates interacted. Some erupted lava that spread across the land. Others released ash and gases into the atmosphere. Volcanic materials mixed with sediments and later became part of the geological record. Earthquakes also occurred as tectonic plates moved. although no direct record of individual earthquakes remains, faults and broken rock layers provide evidence that Earth's crust experienced repeated movement during this period. The Carboniferous landscape included wide plains, hills, mountains, river valleys, coastal swamps, inland basins, forests, deserts in some regions, glaciers, and shallow seas. Each environment supported different forms of life depending on local conditions such as temperature, rainfall, soil, and water availability. Sedimentary basins formed where Earth's crust slowly sank. These low areas collected thick layers of mud, sand, limestone, and plant remains. Over millions of years, the pressure from newer layers compressed older sediments into solid rock. Many important fossil discoveries have been made in these ancient basins. Limestone formed in many shallow marine environments. Tiny marine organisms, shells, corals, and other sea animals contributed calcium-rich material that accumulated on the sea floor. Over long periods, these deposits hardened into limestone, preserving many fossils. Sandstone formed where rivers, beaches, and deserts deposited sand. Shale formed from fine mud that settled in calm water. Coal formed mainly from buried plant material. Together, these different rock types record the changing geography of the Carboniferous world. Glaciers left important evidence across Gondwana. As ice moved, it carved grooves into bedrock and carried rocks over long distances. When glaciers melted, they left behind mixtures of clay, sand, gravel, and large stones. These deposits allow scientists to identify areas that were once covered by ice. The movement of continents during the Carboniferous period happened at rates too slow for humans to notice if they had been present. Each year the land shifted only a very small distance. Over millions of years, however, these small movements completely changed Earth's geography. As continents approached one another, some oceans became narrower. As continents separated in other regions, new ocean basins slowly formed. This continuous movement remains one of the most important processes shaping Earth's surface. The position of the continents also affected ocean circulation. Ocean currents carried heat from one region to another, influencing coastal climates and marine ecosystems. Changes in continental positions gradually altered these currents over millions of years. Many ancient coastlines can still be recognized through geological studies. Layers of marine fossils found far inland show that shallow seas once covered those areas. Ancient river deposits reveal where rivers once flowed, across landscapes that have long since disappeared. The Carboniferous world contained many environments that no longer exist in exactly the same form. The great coal swamps covered enormous areas near the equator. Dense forests stretched across wet lowlands, while glaciers covered distant southern regions. Wide, shallow seas spread over continental interiors before retreating again. Geologists study the geography of the Carboniferous period by examining rocks, fossils, minerals, ancient soil layers, and the arrangement of mountain belts. They also use information from magnetic minerals preserved inside rocks. These minerals record the direction of Earth's magnetic field when the rocks formed, helping scientists estimate where continents were located long ago. Fossils provide additional evidence about ancient geography. Similar plant and animal fossils found on continents now separated by oceans show that these lands were once connected. Matching rock layers and mountain belts also support this understanding of continental movement. Coal deposits remain one of the clearest geographical records of the Carboniferous period. Their wide distribution shows where extensive swamp forests once existed. because coal forms under specific environmental conditions. These deposits reveal information about rainfall, temperature, and landscape features. Ancient soils also provide important evidence. Different soil types formed under different climates. Some indicate wet tropical conditions, while others show cold environments influenced by glaciers. Together, they help reconstruct the geography of the Carboniferous world. The distribution of plant fossils shows that large forests covered much of the equatorial regions. Fossils of seed ferns, giant club mosses, horsetails, and early conifers appear in many areas that once shared similar climates, despite now being separated by oceans. Marine fossils reveal the extent of shallow seas. Fossils of brachiopods, crinoids, corals, mollusks, and other sea animals occur in rocks that formed beneath ancient oceans. Their locations help scientists map the coastlines of the Carboniferous period. The geography of the Carboniferous world continued changing throughout the entire period. No continent remained completely fixed. Coastlines shifted, mountains rose, rivers changed course, glaciers advanced and retreated, and shallow seas repeatedly spread across lowlands before withdrawing again. Some regions experienced repeated flooding from nearby seas. Each flooding event left marine sediments over older river or swamp deposits. Later, when sea levels dropped, forests returned to these same areas. This created repeating layers of coal, shale, sandstone, and limestone that are commonly found in Carboniferous rock sequences. The arrangement of mountains influenced rainfall across many regions. Moist air rose over mountain slopes, leading to increased rainfall in some places. Areas farther away sometimes became much drier because less moisture reached them. These regional differences influenced the kinds of plants and animals that could survive. Large lowland basins remained especially important throughout the Carboniferous period. Their flat landscapes collected water, sediments, and plant material over very long periods. These basins became centers for coal formation and fossil preservation. Many valleys were carved by rivers flowing from highlands into lower plains. These rivers slowly widened their valleys through erosion while also building floodplains by depositing sediment during seasonal floods. Some coastal regions developed broad deltas, where rivers entered shallow seas. As river currents slowed, sand and mud settled to the bottom, gradually extending the coastline outward. Plants often colonized these new areas, eventually creating fresh swamp environments. At the beginning of the Carboniferous period, much of the world had a warm climate. Large areas of land were located close to the equator, where temperatures stayed high for most of the year. Warm weather allowed plants to grow quickly and in great numbers. Thick forests spread across wide lowlands, where rivers moved slowly and where water collected in shallow wetlands. Rain fell often in many of these regions, keeping the soil wet and allowing giant forests to continue growing. The atmosphere during the Carboniferous period was different from the atmosphere that exists today. One of the biggest differences was the amount of oxygen in the air. Scientists believed that oxygen levels slowly increased during much of the Carboniferous period. By the later part of the period, oxygen made up a much larger part of the atmosphere than it does today. This increase happened because enormous forests produced oxygen through photosynthesis. Plants took in carbon dioxide from the air and used sunlight to make food. During this process, they released oxygen into the atmosphere. Normally, when plants die, bacteria and fungi break down their remains. This process returns much of the carbon back into the atmosphere as carbon dioxide. During the Carboniferous period, however, huge amounts of dead plant material collected in waterlogged swamps where there was very little oxygen in the soil. Because the ground stayed wet, dead plants did not fully decay. Layer after layer of plant material built up over long periods of time. Later, these layers were buried beneath sand, mud, and other sun sediments. Great pressure and heat slowly changed this buried plant material into coal. The formation of coal had an important effect on the atmosphere. Since so much carbon became trapped underground, instead of returning to the air, the amount of carbon dioxide in the atmosphere slowly fell. At the same time, plants continued releasing oxygen. As a result, oxygen levels increased while carbon dioxide levels became lower than they had been earlier in Earth's history. Higher oxygen levels affected many forms of life. Animals that breathed air found it easier to obtain oxygen with every breath. Insects were among the creatures that benefited from these conditions. Their bodies used tiny openings called spiracles to let oxygen enter. From there, oxygen moves through small tubes directly to the tissues. This system works well when oxygen levels are high. During the Carboniferous Period, some insects reached sizes much larger than most insects living today. Scientists believed that the rich supply of oxygen was one of the reasons this was possible. Large dragonfly relatives flew through the forests with wings much longer than those of modern dragonflies. Giant millipedes moved across the forest floor, feeding on dead plant material. Other insects also reached impressive sizes. Although oxygen was not the only reason for their growth, it played an important part in allowing these animals to survive and remain active. The climate during the Carboniferous Period was not the same everywhere. Conditions depended on location. Areas near the equator were usually warm and wet. Heavy rainfall supported thick forests filled with giant club mosses, horsetails, seed ferns, and early trees. Rivers often flooded these forests, leaving fresh layers of mud that covered fallen plants. These repeated floods helped create the thick deposits of plant material that later became coal. Farther away from the equator, conditions became drier in many places. Some regions experienced seasons with changing rainfall. Certain areas had open woodlands instead of dense swamp forests. Plants growing there had to survive periods when less water was available. Their leaves, roots, and stems slowly adapted to these different conditions. The southern part of the world experienced another important change. During much of the later Carboniferous Period, large ice sheets developed across the southern supercontinent known as Gondwana. This enormous landmass included areas that are now parts of South America, Africa, Antarctica, Australia, the Indian subcontinent, and nearby regions. Thick glaciers spread across parts of this land. Evidence of these glaciers can still be seen today in scratches left on ancient rocks, deposits of stones carried by moving ice, and layers of sediment formed by melting glaciers. The development of these glaciers shows that parts of Earth became much colder than before. As more water became locked inside the growing ice sheets, sea levels fell. Large areas of shallow seafloor became dry land. Coastlines moved outward, and many marine habitats disappeared. Later, when glaciers melted, sea levels rose again and flooded coastal regions. These repeated changes affected both life on land and life in the oceans. The movement of continents also influenced the climate. During the Carboniferous Period, Earth's continents continued moving because of plate tectonics. Many landmasses slowly came together to form larger continents. Mountains rose where continents collided. These growing mountain ranges changed wind patterns and rainfall. Mountains forced moist air upward, where it cooled and formed rain. Areas on the opposite side often became drier because much of the moisture had already fallen. Mountain building also affected rivers. New mountains provided fresh rock that rivers slowly wore away. sediments carried by rivers spread across valleys, floodplains and coastal regions. These sediments buried plant remains and helped preserve them for millions of years. Many important coal deposits formed in such environments. The oceans also influenced climate during the Carboniferous Period. Ocean currents moved warm and cool water around the planet. These currents affected temperatures along coastlines and influenced rainfall. Changes in the arrangement of continents sometimes altered the paths of ocean currents, leading to changes in regional climates. The amount of carbon dioxide in the atmosphere remained closely connected to climate. Carbon dioxide traps heat in the atmosphere. When carbon dioxide levels decreased because large amounts of carbon became buried in coal, Earth's climate gradually cooled. This cooling helped glaciers expand across southern regions. At the same time, warm tropical climates continued near the equator because of their position on the planet and the strong sunlight they received throughout the year. The Carboniferous atmosphere also contained nitrogen, which remained the largest part of the air just as it does today. Nitrogen plays an important role in supporting life, even though most living things cannot use atmospheric nitrogen directly. Certain bacteria change nitrogen into forms that plants could absorb from the soil. Plants then used these nutrients to grow. Animals received nitrogen by eating plants or by eating other animals. Rainfall during the Carboniferous Period varied from place to place and changed over time. In tropical wetlands, rain fell often enough to keep swamps filled with water. Rivers overflowed their banks and spread fresh sediment across the landscape. Wet conditions allowed forests to grow without long periods of drought. These forests contained many kinds of plants, including giant club mosses, tall horsetails, seed ferns, chordates, and early conifers. The leaves, branches, roots, and trunks of these plants created thick layers of organic matter on the forest floor. Water covered much of this material before it could fully decay. This slow burial preserved enormous amounts of carbon. Over millions of years, the continued growth and burial of forests created many of the coal deposits that people mine today. Storms were also part of the Carboniferous climate. Warm, moist air often produces powerful storms. Although scientists cannot observe these ancient storms directly, evidence from rock layers suggests that rivers sometimes flooded suddenly. Floodwaters carried sand and mud across swamp forests. Fallen trees became buried beneath sediments. These buried forests can still be found as fossilized tree stumps and plant remains inside ancient rock layers. Seasonal changes existed in many regions. Some places experienced wet seasons followed by drier seasons. Plants adapted to these changes in different ways. Some developed deeper roots to reach water below the surface. Others produced seeds that could survive less favorable conditions until rain returned. As the Carboniferous Period continued, climate changes became more noticeable. Some swamp forests disappeared as conditions became drier. Other forests survived only in certain areas where enough water remained available. New plant groups became more common in places with lower rainfall. Early seed plants spread into habitats that were less suitable for plants needing constant moisture. The changing climate also affected animals. Amphibians depended heavily on water because they laid soft eggs that dried out easily. Wet environments allowed them to remain widespread in swamp forests and along rivers. As some regions became drier, reptiles gained an advantage. Their eggs contained protective coverings that reduced water loss. This adaptation allowed reptiles to reproduce farther from lakes, rivers, and swamps. The atmosphere influenced fire as well. Oxygen supports burning. When oxygen levels become higher, fires can spread more easily if dry plant material is available. Scientists have found fossil charcoal in Carboniferous rocks, showing that wildfires occurred during this period. Even though many forests remained wet, dry seasons and local weather conditions sometimes allowed fires to start. Lightning from storms probably ignited some of these fires. Wildfires changed forest ecosystems. They cleared vegetation from certain areas, leaving open ground where new plants could grow. Different plant species responded in different ways after fires. Some recovered quickly, while others spread into newly opened spaces. These natural cycles helped shape local environments. The cooling climate in southern regions continued influencing global conditions. Large ice sheets reflected sunlight back into space because of their bright surfaces. This helped maintain cooler temperatures in glaciated areas. The repeated growth and melting of glaciers caused sea levels to rise and fall many times during the Carboniferous Period. Each change altered coastlines, river systems, wetlands, and shallow seas. Marine life responded to these changing conditions. When sea levels rose, shallow seas spread across low-lying land, creating new habitats for marine organisms. When sea levels fell, these habitats became smaller or disappeared. Many marine species adapted to these repeated environmental changes over long periods. Scientists learn about Carboniferous climates by studying several kinds of evidence. Ancient soils reveal information about rainfall, temperature, and plant growth. Coal deposits show where large swamp forests once existed. Fossil leaves provide clues about moisture levels because leaf shape often reflects environmental conditions. Growth rings inside fossil wood sometimes reveal seasonal changes in climate. Chemical studies of ancient rocks help estimate temperatures and atmospheric gases. Tiny fossils found in marine rocks also provide important information. Shells from ancient sea animals contain chemical signals that reflect the temperature and composition of seawater when the animals were alive. By studying these signals, scientists can estimate changes in ocean temperatures during different parts of the Carboniferous Period. Ice deposits preserved in ancient rocks offer direct evidence of glacial activity. Large stones carried by glaciers and dropped into fine sediments reveal the movement of ice across the landscape. Scratches carved into bedrock by moving glaciers show the direction in which the ice traveled. Together, these clues allow scientists to reconstruct ancient climates with increasing accuracy. The position of Earth itself also influenced Carboniferous climate. Earth's axis was tilted then, just as it is today. This tilt created seasons, although the strength of seasonal changes depended on latitude. Areas close to the equator experienced relatively small temperature changes throughout the year, while regions farther from the equator experienced greater seasonal differences. The length of days and years was also slightly different, because Earth's rotation has gradually slowed over millions of years. During the Carboniferous Period, days were a little shorter than they are today. Although this difference had only a limited effect on climate, it formed part of the natural conditions experienced by living organisms. Volcanic activity influenced atmospheric conditions from time to time. Volcanoes release gases, including carbon dioxide, water vapor, and sulfur compounds into the atmosphere. Large volcanic eruptions sometimes affected climate by adding tiny particles that reflected sunlight for short periods. Over longer times, volcanic carbon dioxide could contribute to warming, although the extensive burial of plant material during the Carboniferous helped reduce atmospheric carbon dioxide overall. The balance between volcanic emissions and carbon burial changed slowly over millions of years. Earth's climate responded to these long-term shifts rather than to sudden changes alone. Natural systems involving the atmosphere, oceans, rocks, plants, and living organisms remained closely connected throughout the Carboniferous Period. Humidity remained high in many tropical regions. Moist air supported thick vegetation and encouraged rapid plant growth. Ferns, club mosses, horsetails and seed plants competed for sunlight in crowded forests. Fallen leaves and branches covered the wet ground. Countless insects, amphibians, spiders and other small animals lived among the dense vegetation. The thick forests themselves influenced local climate. Plants released water vapor into the air through tiny openings in their leaves. This process increased humidity and contributed to cloud formation. Clouds often brought additional rainfall, helping maintain the wet conditions needed by the forests. Different river systems shaped local climates as well. Slow-moving rivers created broad floodplains where water spread across large areas after heavy rains. Standing water remained in shallow depressions for long periods. These wetlands became ideal places for plant growth and coal formation. Faster rivers carried sediments farther across the landscape, constantly reshaping valleys and floodplains. Many Carboniferous forests existed near coastlines where rivers entered shallow seas. These coastal environments experienced changes as sea levels rose and fell. Salt water sometimes entered freshwater swamps, changing the kinds of plants and animals that could survive there. When sea levels dropped again, freshwater conditions returned. The climate affected the distribution of oxygen within lakes and swamps. Warm, still water often contained less dissolved oxygen than flowing water. Different aquatic animals adapted to these conditions in various ways. Some species thrived in quiet wetlands, while others preferred rivers with moving water. Microorganisms also played an important role in Carboniferous ecosystems. Bacteria and fungi helped recycle nutrients from dead plants and animals. Although waterlogged conditions slowed decay in many swamps, decomposition still occurred. The speed of decay depended on oxygen levels, moisture, temperature, and the activity of microorganisms. The interaction between climate, atmosphere, plants, animals, rocks, water, and microorganisms formed a complex natural system. Every part influenced the others. Changes in rainfall affected forests. Forests influenced atmospheric gases. Atmospheric gases affected temperature. Temperature influenced glaciers. Glaciers changed sea levels. Sea levels altered habitats for both marine and land organisms. Throughout the Carboniferous period, these natural processes continued without stopping. Conditions did not remain exactly the same for millions of years. Warm intervals alternated with cooler intervals. Wet environments expanded and contracted. Forests spread across new regions and disappeared from others. Glaciers advanced and retreated. Rivers changed their paths. Coastlines shifted as sea levels changed. During the Carboniferous period, one of the most important natural features on Earth was the spread of huge swamp forests across many parts of the land. These wet forests covered enormous areas for a very long time. They became the places where the plant material that later turned into coal first gathered. The process that created these coal swamps happened slowly over millions of years. It depended on the climate, the movement of the land, the amount of rain, the flow of rivers, the level of the seas, and the steady growth of plants. Every part of this long process helped create the conditions that allowed thick layers of dead plants to collect instead of completely breaking down. The Carboniferous period began about 359 million years ago and ended about 299 million years ago. During much of this time, the climate across many regions was warm and very wet. Rain fell often, and large amounts of water stayed on the land instead of quickly flowing away. Many areas remained flooded for long periods. Rivers slowly carried water across wide plains, while lakes, marshes and shallow pools spread across the low ground. Since much of the land was flat, water moved very slowly. This allowed wetlands to grow larger and remain stable for very long periods. The continents were arranged differently from the way they are today. Large landmasses slowly moved because of the movement of Earth's crust. As these continents shifted, many regions were located close to the equator. Places near the equator usually received strong sunlight throughout the year. Warm temperatures helped plants grow continuously. The frequent rainfall also provided the water that plants needed. Because there were no long cold seasons in many of these areas, plants continued growing for much of the year. Many of the low-lying regions were located close to rivers and shallow coastal areas. Rivers often overflowed their banks after heavy rainfall. When this happened, water spread across nearby land and left behind fine mud and other sediments. These materials slowly built up over time. After the floodwaters became calm, new plants quickly grew across the wet ground. This cycle happened again and again. Each flood added new layers of sediment while fresh plants covered the surface. The ground in these wetlands remained soft and rich in water. The soil stayed wet because there was very little slope for water to flow away. In many places, the water table remained close to the surface. Rainwater, river water, and groundwater all helped keep the land saturated. Plants growing in these conditions developed roots that spread through the wet soil while their stems and leaves reached toward the sunlight above. The forests that covered these swamps looked very different from forests today. Flowering plants had not yet appeared. Instead, giant club mosses, horsetails, seed ferns, tree ferns, and other early plants formed thick forests. Many of these plants reached great heights. Their trunks stood close together, creating dense forests with very little open ground between them. Thick layers of leaves, branches, roots, and fallen trunks covered the swamp floor. Many of these ancient plants reproduced by releasing spores instead of seeds. Spores were carried by the wind or by water. When they landed in suitable wet places, they grew into new plants. The constant supply of water allowed these plants to spread across large areas. As older plants died, younger ones took their place. The forests remained active for countless generations of plant life. The amount of plant growth during this period was very high. Warm temperatures, abundant sunlight, and frequent rainfall allowed plants to produce large amounts of leaves, stems, roots, and wood. Every year, more plant material was added to the swamp floor. Some plants fell because of old age, disease, storms, or changing water levels. Others died naturally after completing their life cycle. All of this dead plant material slowly collected on the wet ground. In many modern environments, dead plants quickly rot because bacteria and fungi break them down. During much of the Carboniferous Period, however, the conditions inside many swamps slowed this process. The ground remained covered by water for long periods. Waterlogged soil contained very little oxygen. Many organisms that normally break down dead plants could not work as effectively without enough oxygen. As a result, much of the fallen plant material remained only partly broken down. Each new generation of plants grew on top of the older layers. More leaves fell, more branches broke off, more trunks collapsed into the water. Roots became buried beneath fresh layers of plant material and mud. Slowly, thick deposits of dead plants built up over many thousands of years. These deposits became known as peat. Peat formed when dead plants collected faster than they could fully decay. It remained soft, dark, and rich in organic material. Peat was not yet coal. It still contained large amounts of water and plant remains. However, It was the first important step in the long process that eventually produced coal. The formation of peat required stable conditions over very long periods. If the swamps had dried out too often, much of the plant material would have decayed completely. If rivers had washed away the plant remains, thick peat layers would not have formed. Instead, the land remained wet enough to protect much of the dead vegetation, while allowing new forests to continue growing above it. Floods played an important part in this process. Rivers regularly carried sand, mud, and fine clay into the swamps. Sometimes these materials covered the peat with a fresh layer of sediment. New plants later grew on top of this sediment. Over time, another thick layer of peat formed above it. This repeated cycle created many separate coal layers stacked one above another. In some regions, geologists have discovered long sequences, showing repeated layers of sandstone, shale, coal, and other sedimentary rocks. Each layer records another period of swamp growth followed by flooding and burial. Changes in sea level also affected the formation of coal swamps. During parts of the Carboniferous Period, shallow seas spread across low coastal regions. Later, the seas moved back, leaving new land exposed. Plants quickly spread across these fresh surfaces. Wetlands developed once again, and peat began to collect. These repeated changes between land and shallow seas helped create many different coal-forming environments. Earth's crust was also slowly changing. Some regions gradually sank while others slowly rose. Areas that slowly sank often became ideal places for thick peat deposits to develop. As the land moved downward, there was always room for more plant material and sediment to collect. Without this slow sinking, the growing peat might eventually have risen above the water level and dried out. Instead, the land continued providing space for new layers to build up. The slow movement of Earth's crust also affected rivers. Rivers changed direction over long periods, creating new channels and leaving older ones behind. Abandoned river channels often filled with water and became wetlands. New forests soon covered these areas. Fresh peat deposits began to form wherever conditions remained wet enough. Storms sometimes damaged the forests. Strong winds knocked down large trees. Heavy rain increased flooding. Broken branches and fallen trunks collected in pools of water. Instead of completely disappearing through decay, many of these remains became buried beneath mud and fresh plant material. These events added even more organic matter to the growing peat deposits. The roots of swamp plants helped hold the soft ground together. Root systems spread through the wet soil, reducing erosion in many places. As plants died, their roots remained buried beneath younger vegetation. These underground remains became part of the growing peat. Scientists studying coal often find fossil roots preserved in the rocks beneath ancient coal seams. These roots show where the forests once stood. The forests supported many forms of animal life. Early insects lived among the leaves and branches. Some insects reached sizes much larger than many insects alive today, because environmental conditions allowed them to grow well. Amphibians moved through the shallow water, while early reptiles began appearing during the later part of the Carboniferous Period. Many smaller animals lived among fallen leaves, tree roots, and decaying wood. Their activities disturbed parts of the swamp floor, but the huge amount of plant growth continued adding fresh material each year. Microorganisms also lived in the swamps. Some bacteria helped break down dead plant matter. Where oxygen was available, other microorganisms lived in places where oxygen was limited. Their activities slowly changed the chemical makeup of the peat. Although decomposition continued, it happened much more slowly than in dry forests. This slow decay allowed organic material to build up over long periods. chemical changes began almost as soon as plant material became buried. Water filled the spaces between leaves, stems and roots. Some gases escaped into the atmosphere. Minerals dissolved in the water moved through the peat. The buried plant material slowly became more compact as fresh layers collected above it. As more sediment buried the peat, pressure steadily increased. The weight of sand, mud, and other deposits squeezed water out of the peat. The organic material became denser. Over millions of years, heat from deeper parts of Earth's crust also affected these buried layers. The combined effects of pressure, heat, and time slowly changed peat into different kinds of coal. The first stage usually produced lignite, often called brown coal. Continued burial changed lignite into bituminous coal, which became the most common type of coal formed during the Carboniferous Period. Under even greater pressure and heat, some coal eventually became anthracite, which contains more carbon and burns with greater heat. This entire process required extremely long periods of geological time. Not every swamp became coal. Many wetlands disappeared because rivers cut through them. Erosion removed the plant material, or changing environmental conditions prevented peat from collecting. Only certain swamps remained stable long enough for thick peat layers to develop and later become buried beneath sediments. These were the swamps that eventually produced the large coal deposits found today. The thickness of peat required to produce coal was much greater than the thickness of the finished coal seam. As peat lost water and became compressed, it became much thinner. A very thick layer of peat could eventually produce only a much thinner layer of coal. This shows how much plant material originally accumulated inside the ancient swamps. Different plant species contributed different materials to the peat. Leaves, bark, wood, roots, and spores all became mixed together. Some parts resisted decay better than others. Thick bark often survived longer than softer tissues. Woody stems also remained for longer periods. These different materials affected the final structure of the coal that eventually formed. Many coal seams still contain visible remains of ancient plants. Scientists studying polished coal samples sometimes identify preserved bark patterns, spores, wood cells, and other plant structures. These fossils provide valuable information about the forests that existed during the Carboniferous Period. They help researchers understand which plants grew there and how the swamp ecosystems functioned. The water inside the swamps often contained dissolved minerals carried by rivers. These minerals sometimes entered the buried plant material. Iron compounds, clay minerals, and other substances became trapped inside the growing peat. As coal later formed, some of these minerals remained within it. This is one reason why different coal deposits have different chemical compositions. The amount of oxygen in the atmosphere during much of the Carboniferous Period was higher than it is today. The huge forests produced large amounts of oxygen through photosynthesis. Plants use sunlight to produce food from water and carbon dioxide, releasing oxygen into the atmosphere. The widespread growth of forests over millions of years affected the composition of Earth's atmosphere. The removal of carbon dioxide from the atmosphere also played a role. Plants absorbed carbon dioxide while growing. When many of those plants became buried instead of completely decaying, much of their carbon remained locked underground. This process slowly reduced the amount of carbon dioxide returning to the atmosphere. Large amounts of carbon remained stored inside peat and later inside coal. The formation of coal swamps was not limited to one small region. Similar environments developed across many parts of the world wherever conditions were suitable. Ancient tropical regions provided especially favorable environments because warm temperatures and abundant rainfall supported continuous plant growth. Thick coal deposits formed across areas that are now found in North America, Europe, and Asia. Smaller deposits also developed in other parts of the ancient world. Although the forests appeared stable for long periods, they continued changing. Some plant species became more common while others declined. Environmental conditions slowly shifted as rivers changed course. Sea levels rose or fell, and climates varied over long periods. New wetlands appeared while older swamps disappeared beneath sediments or shallow seas. Fire sometimes affected parts of these forests. Lightning could ignite dry vegetation during periods when water levels temporarily dropped. Charcoal preserved inside some coal deposits shows that ancient wildfires occurred from time to time. After fires, new plants often returned as wet conditions became established again. Fresh vegetation gradually covered the burned ground. Volcanic activity also influenced some regions. Volcanic ash sometimes settled across forests far from erupting volcanoes. Thin layers of ash became mixed with swamp sediments. These ash layers provide useful markers for geologists because they can often be dated more accurately than surrounding rocks. They also show that volcanic eruptions occurred while the coal-forming forests were still growing. Seasonal changes existed in many regions, although they were often less extreme than in colder climates. Periods of heavier rainfall increased flooding. Slightly drier periods changed water levels without completely drying the swamps. Plants adapted to these changing conditions and continued growing as long as enough water remained available. The edges of the swamps often blended into river channels, shallow lakes, and slightly higher ground. Different plant communities developed in each area depending on water depth, soil conditions, and sunlight. Plants that tolerated deeper water grew in flooded areas, while others preferred ground that was only partly waterlogged. Together, these plant communities created large wetland ecosystems covering extensive regions. Dead insects, fish, amphibians, and other animals occasionally became buried alongside plant material. Some were rapidly covered by mud after floods. Their remains sometimes became fossils, preserved within rocks associated with coal deposits. These fossils provide valuable evidence about the animals that lived inside and around the coal swamps. The sediments surrounding coal seams contain important information about ancient environments. Sandstone usually records former river channels. Shale often formed from fine mud settling in quiet water. Limestone sometimes indicates periods when shallow seas covered the land. By studying these rock layers together with coal seams, scientists reconstruct the changing landscapes that existed throughout the Carboniferous Period. The development of thick coal deposits required an unusual combination of conditions that remained favorable for millions of years. Plant growth had to remain high, decay had to stay slow, flooding had to bury organic material without destroying it, and Earth's crust had to continue providing space for new sediments and peat. If any of these conditions changed too greatly, coal formation could stop. Many of the coal deposits mined today were created during this remarkable period of Earth's history, because the environmental conditions were especially favorable. Although coal also formed during other geological periods, the Carboniferous became famous for producing some of the largest and most widespread coal deposits ever formed. These deposits preserved enormous amounts of ancient plant material that had once grown inside vast swamp forests, covering the low tropical regions of the ancient world. The evolution and diversity of early forests was one of the most important parts of the long history of life on Earth. Early forests did not appear suddenly. They developed slowly over millions of years as plants changed little by little, and became better able to survive on land. Before forests existed, much of the land was covered by simple plants that stayed close to the ground. These early land plants were very different from the large trees that later covered wide areas. They had no true wood, their stems were small, and they depended on wet places, because they needed water for reproduction. Over a very long time, natural changes allowed plants to grow taller, become stronger, and spread into many different environments. These changes eventually led to the appearance of the first forests. Long before the Carboniferous Period, plants had already started to leave the water and live on land. This was a difficult step because conditions on land were very different from conditions in lakes, rivers, and seas. Plants had to deal with dry air, changing temperatures, strong sunlight, and gravity. They also needed ways to move water from the ground to all parts of their bodies. Early land plants slowly developed new structures that helped them survive these conditions. They formed roots that reached into the soil, stems that supported their weight, and tissues that carried water and nutrients. These developments allowed plants to become larger and stronger than ever before. One of the most important changes in plant evolution was the development of vascular tissue. This special tissue acted as a transport system inside the plant. It moved water and dissolved minerals upward from the roots while carrying food produced by the leaves to other parts of the plant. Because of this system, plants no longer had to remain very small. They could grow higher above the ground and produce more leaves. Taller plants also received more sunlight, which helped them make more food through photosynthesis. As generations passed, many kinds of vascular plants appeared, each with its own special features. Wood also became an important part of plant evolution. Wood gave strength to stems and trunks, allowing plants to stand upright without falling over. As wood became thicker and stronger, plants reached greater heights than ever before. Their branches spread in many directions, creating larger crowns filled with leaves. These leaves captured sunlight efficiently, supporting rapid growth. The development of wood also helped plants live longer, because their strong trunks could survive for many years while continuing to grow. Roots became deeper and more complex as plants evolved. Early roots mainly held plants in place, but later roots also absorbed large amounts of water and nutrients from the soil. Some roots spread widely near the surface, while others reached deep underground. This made it possible for plants to survive during periods when water near the surface became limited. Deep roots also helped break apart rocks, beginning the long process of soil formation. As roots grew and died over many generations, they added organic matter to the ground, making soils richer and more suitable for other plants. Leaves also changed greatly during the evolution of forests. The earliest leaves were usually small and simple. Over time, plants developed larger leaves with many veins, carrying water and nutrients throughout the leaf. Larger leaves increased the amount of sunlight that plants could capture. This allowed them to produce more food and grow more quickly. Different groups of plants developed different leaf shapes, sizes, and arrangements. These differences helped various species survive in different environments, with different amounts of sunlight and moisture. The first forests were very different from forests that exist today. Many familiar flowering trees had not yet evolved. Instead, forests were filled with ancient groups of plants that are now rare or completely extinct. Giant club mosses were among the tallest plants. Although their smaller relatives still exist today, the ancient forms reached enormous heights and formed thick forests across large regions. Their trunks were covered with special patterns left by fallen leaves, and their branches often carried long narrow leaves near the top. Another important group included giant horsetails. Modern horsetails are small plants that usually grow near wet places, but their ancient relatives became tall tree-like plants. Their stems were divided into many sections and branches grew in circles around each joint. These plants reproduced by releasing spores instead of seeds. They often grew together in wet soils where water was plentiful throughout much of the year. Large ferns also became major members of early forests. Many ancient ferns were much larger than the ferns found today. Some developed thick trunks and formed tree ferns that reached impressive heights. Their crowns were filled with large divided leaves that spread outward in every direction. These leaves collected sunlight while also producing spores that allowed new plants to grow. Ferns became common because they could reproduce successfully in the warm and wet environments that covered many parts of the earth. Seed ferns represented another important stage in plant evolution. Although they looked similar to ordinary ferns because of their leaves, they reproduced with seeds instead of spores. This was an important change because seeds protected the developing young plant and stored food that supported early growth. Seeds also allowed plants to survive dry conditions better than spores alone. Seed ferns became successful members of many forests and helped prepare the way for later groups of seed-producing plants. Early gymnosperms also appeared during this long period of plant evolution. These plants produced seeds without flowers or fruits. Their seeds often developed in cones or other protective structures. Gymnosperms became increasingly important because they could reproduce in a wider range of environments. Unlike spore-producing plants, they did not depend as heavily on standing water for reproduction. This allowed them to spread into regions that experienced seasonal dryness. The spread of forests changed the appearance of the land. Areas that had once been open and covered mainly with small plants gradually became filled with tall trunks, thick branches, and broad canopies. Sunlight reaching the ground became more limited because much of it was blocked by leaves above. New environments developed beneath the trees where shade-loving plants could survive. Mosses, small ferns, fungi, and many other organisms found suitable places to live on the forest floor. The forest floor became rich in fallen leaves, branches, bark, and dead plants. As these materials broke down, they released nutrients back into the soil. Tiny organisms, including fungi and bacteria, played an important role in this process. They broke dead material into simpler substances that living plants could absorb through their roots. This continuous movement of nutrients supported the growth of dense forests over very long periods. Not all dead plant material decayed completely. In many swampy environments, water covered the ground and slowed decomposition. Dead plants accumulated layer upon layer because bacteria and fungi could not fully break them down in the oxygen-poor conditions. Over extremely long periods, these thick layers were buried beneath sediments. Heat and pressure slowly changed the buried plant material into coal. Much of the coal used by humans today was formed from these ancient forests. The climate during much of the Carboniferous period supported the growth of vast forests. Many regions experienced warm temperatures and abundant rainfall throughout most of the year. Rivers frequently overflowed their banks, creating wetlands and swamps where water remained for long periods. These conditions allowed moisture-loving plants to grow rapidly and reach very large sizes. The combination of warmth, water, and fertile soils created environments where forests spread across wide areas. The atmosphere also played a role in forest development. Oxygen levels became much higher than they are today, because forests produced enormous amounts of oxygen during photosynthesis. At the same time, plants removed large amounts of carbon dioxide from the atmosphere and stored carbon within their trunks, roots, leaves, and buried remains. These changes influenced the atmosphere and affected the global environment over very long periods. Different forests developed in different parts of the world depending on local conditions. Some forests grew in low-lying swamps that remained flooded for much of the year. Others developed on better drained ground where soils stayed moist without becoming completely waterlogged. Some regions experienced seasonal changes in rainfall, allowing plants adapted to those conditions to become established. These differences created many kinds of forest communities with different mixtures of plant species. Competition among plants became increasingly important as forests became denser. Every plant needed sunlight, water, nutrients, and space. Taller trees often received more sunlight than shorter plants. Smaller plants adapted by growing quickly before taller trees shaded them or by surviving in low-light conditions beneath the canopy. Roots spread through the soil searching for water and nutrients. Different species developed different strategies that allowed many kinds of plants to live together. The growth of forests also influenced animal evolution. Dense vegetation provided food, shelter, nesting places, and protection from predators. Many insects fed on leaves, stems, spores, and wood. Some insects laid their eggs inside plant tissues where developing young could feed safely. Other insects helped break down dead wood and fallen leaves. As plant diversity increased, insect diversity also expanded because different insects specialized on different plants. Large dragonflies and many other winged insects became common inhabitants of these forests. High oxygen levels may have supported the evolution of unusually large insects. Forests provided places where flying insects could feed, rest, reproduce, and avoid danger. Their movements among plants also influenced the spread of spores and other plant materials, although most early plants still depended mainly on wind for reproduction. Spiders, early relatives of modern millipedes, centipedes, and many other small animals, lived among fallen leaves and decaying wood. They fed on insects or dead organic matter. Their activities helped break plant material into smaller pieces, making decomposition easier for fungi and bacteria. Countless small organisms formed complex communities within the soil and leaf litter. Early amphibians also benefited from expanding forests. Many amphibians required water for reproduction, and swamp forests provided many ponds, streams, and marshes where eggs could develop. Dense vegetation protected them from drying out while providing many places to hide. Amphibians hunted insects and other small animals among the plants, becoming important members of forest ecosystems. As forests continued evolving, reptiles gradually appeared. Their eggs could survive away from open water because protective coverings reduced water loss. This allowed reptiles to move farther from swamps into drier environments while still depending on forests for food and shelter. The spread of forests therefore supported important changes in animal evolution as well as plant evolution. The structure of early forests became increasingly complex. Tall trees formed an upper canopy that received the strongest sunlight. Beneath this layer grew smaller trees and young plants, waiting for openings where more light could reach them. Shrubs, ferns, mosses, fungi, and many smaller plants covered the ground. Dead trunks provided homes for insects, fungi, and other organisms. Every level of the forest supported different forms of life. Storms, floods, fires, and changing river channels regularly affected forests. Strong winds sometimes knocked down large trees, opening spaces where sunlight reached the ground. Seeds and spores quickly established new plants in these openings. Floods buried some forests beneath layers of mud, while creating new wetlands elsewhere. These natural disturbances constantly changed the arrangement of forest communities while allowing new growth to begin. Plant reproduction became increasingly diverse as forests evolved. Many early plants still reproduced with spores released into the air. Spores were extremely small and could travel long distances by wind before landing in suitable places. However, they required wet conditions for successful reproduction. Seed-producing plants gained an advantage because seeds contained stored food and protective coverings. They could survive longer before growing and often succeeded in environments where spores were less effective. The evolution of pollen was another important development. Pollen carried male reproductive cells without requiring freestanding water for movement. Wind transported pollen from one plant to another over considerable distances. This made reproduction more successful in many environments and allowed seed plants to spread into wider regions. The development of bark protected tree trunks from injury, drying, and disease. Thick bark reduced water loss while shielding living tissues inside the trunk. Some trees also developed protective chemicals that discouraged animals from feeding on them. These defenses increased survival and allowed trees to live for many years. Different plant groups continued evolving side by side. Some ancient groups remained successful for millions of years before disappearing. Others gave rise to later forms that still exist today. Evolution did not follow a single path. Many branches of plant history developed at the same time, each responding to changing environmental conditions in different ways. The arrangement of continents influenced forest distribution. Land masses slowly moved because of processes within the Earth. As continents shifted, climates changed. Some regions became wetter, while others became drier. Mountain building altered rainfall patterns and created new environments. Forests expanded or retreated as conditions changed, and different plant communities became separated from one another. Over long periods, isolated populations evolved into new species. Volcanic activity occasionally affected forests by covering large areas with ash or lava. Although such events destroyed local vegetation, they also created fresh surfaces where new plants eventually became established. Weathering slowly broke volcanic rocks into soil that later supported new forests. Plant communities repeatedly recovered after natural disturbances over geological time. The interaction between forests and the atmosphere continued throughout this period. Growing forests absorbed carbon dioxide during photosynthesis and released oxygen. Dead plants stored carbon underground when buried before complete decay. These long-term processes influenced global carbon cycles and affected climate over millions of years. Water cycles were also influenced by expanding forests. Tree roots absorbed large amounts of water from the soil, while leaves released water vapor into the air through tiny openings. This movement of water affected local humidity and rainfall patterns. Forests also slowed the movement of rainwater across the ground, reducing soil erosion and allowing more water to enter the soil. Soils became increasingly complex because of continuous plant growth. Dead roots, leaves and wood mixed with minerals from weathered rocks. Earth materials became richer in nutrients, supporting even greater plant diversity. Microorganisms living within the soil formed partnerships with plant roots, helping plants absorb nutrients more efficiently while receiving food from the plants. Fungi became especially important members of forest ecosystems. Many fungi formed close relationships with roots, extending fine threads through the soil. These threads absorbed water and minerals that roots alone could not easily reach. In return, plants supplied sugars produced during photosynthesis. These partnerships improved plant growth and supported the development of healthy forests. Different forest regions often contained different dominant species. Wet swamps favored giant club mosses, horsetails, and tree ferns. Better drained areas supported increasing numbers of seed ferns and early gymnosperms. Riverbanks, floodplains, and uplands each developed characteristic plant communities depending on water availability, soil conditions, and sunlight. Plant fossils provide much of what scientists know about these ancient forests. Fossilized trunks, leaves, spores, seeds, roots, and pollen have been discovered in rocks formed during the Carboniferous Period. Some fossil forests remain standing where they originally grew before being buried by sediments. These discoveries help scientists understand how ancient forests looked, how plants were arranged, and how they changed through time. Microscopic fossils are also valuable sources of information. Fossil spores and pollen preserved in rocks reveal which plant groups lived in particular regions. Because spores and pollen spread widely through the air, they are often found even where larger plant fossils are absent. Scientists use these tiny remains to reconstruct ancient environments and follow changes in vegetation across different time periods. Growth rings preserved in fossil wood sometimes provide clues about environmental conditions. In regions with changing seasons, trees often formed visible growth rings that recorded periods of faster and slower growth. By studying fossil wood, scientists learn about ancient climates and seasonal changes that affected forest development. Chemical studies of fossil plants also provide important information. The remains of ancient plant tissues preserve evidence about atmospheric conditions, water availability, and nutrient cycles. Combined with geological evidence, these studies allow researchers to build detailed pictures of ancient forest ecosystems. The diversity of early forests continued increasing because evolution constantly produced new forms, while environmental changes created new opportunities. Some plants specialized in living in permanently wet swamps. Others adapted to drier uplands or seasonal climates. Different leaf shapes, root systems, reproductive methods, and growth patterns allowed many species to exist together without occupying exactly the same environments. Young forests often developed after floods or other disturbances cleared existing vegetation. Pioneer plants quickly occupied open ground, stabilizing soils and creating conditions suitable for larger species. Over time, additional plant groups entered these developing forests until mature communities became established. This continuous process occurred repeatedly across changing landscapes. Large amounts of plant material produced by forests supported rich food webs. Plant-eating insects fed on leaves, stems, spores, seeds, and wood. Predators hunted these insects. Dead organic matter nourished fungi, bacteria, worms, and countless small animals. Nutrients moved continuously between living organisms and the soil, supporting long-lasting ecosystems. The development of forest also changed river systems. Roots stabilized riverbanks and reduced erosion. Fallen trunks sometimes blocked streams, creating ponds and wetlands. Organic matter washed into rivers supported aquatic organisms. Forests therefore influenced both land and freshwater environments. Many ancient forests disappeared as climates gradually changed toward the end of the Carboniferous Period. Some swamp regions dried, reducing habitats for moisture-loving plants. Seed-producing plants adapted better to these changing conditions and became increasingly important. Although many ancient plant groups eventually declined or disappeared, their evolutionary developments continued influencing later forests throughout Earth's history. During the Carboniferous period, amphibians experienced one of the greatest periods of growth and expansion in their history. Amphibians had first appeared during the late Devonian period, but they became far more successful during the Carboniferous. Over millions of years, they evolved into many different forms. Some remained small and lived among fallen leaves, mosses, and shallow pools. Others became medium-sized hunters that searched for insects, spiders, worms, fish, and other small animals. A few species grew into very large predators that reached several meters in length and occupied the top of freshwater food chains. The enormous forests of the Carboniferous supported huge populations of insects and other invertebrates. Oxygen levels in the atmosphere were much higher than today, allowing many insects to grow to unusually large sizes. Giant dragonfly relatives, enormous millipedes, and many other arthropods became common sources of food for amphibians. Fish were also plentiful in rivers and swamps, giving larger amphibians another important food source. Although amphibians spread widely across the land, they still depended heavily on water. Their thin, moist skin dried out easily, so they usually stayed close to rivers, ponds, lakes, marshes, and swamps. Most species returned to water to reproduce. Their eggs lacked a protective shell and had to remain moist to survive. After hatching, many young amphibians lived as aquatic larvae with gills before gradually developing lungs and limbs as they matured. The bodies of Carboniferous amphibians continued to evolve. Their legs became stronger, allowing better movement across muddy ground and through dense vegetation. Their ribs and backbone provided greater support for life on land, while their lungs became more effective at breathing air. Even so, many species still breathed partly through their moist skin. The Carboniferous saw the appearance of many different amphibian groups. Some had long bodies with short legs and spent much of their lives in water. Others had broader heads, stronger limbs, and spent more time on land, although they rarely moved far from wet habitats. Their skulls became more specialized for catching different kinds of prey, and their teeth helped them grip slippery animals. Predators also became more common during this period. Large amphibians hunted fish, smaller amphibians insects and other animals living in freshwater habitats. At the same time, they had to avoid larger predators, including certain fishes and the earliest reptiles that began appearing during the later part of the Carboniferous. The spread of amphibians also played an important role in Carboniferous ecosystems. They helped control populations of insects and other small animals while serving as food for larger predators. Their movement between water and land linked freshwater and terrestrial environments, allowing energy and nutrients to move through different parts of the ecosystem. Toward the end of the Carboniferous period, a major evolutionary change occurred with the rise of the first true reptiles. Unlike amphibians, reptiles developed waterproof skin and eggs protected by strong shells, allowing them to reproduce away from water. These adaptations enabled reptiles to spread into drier environments, where amphibians could not easily survive. Even though reptiles gradually became more successful in many habitats, amphibians remained widespread and continued to thrive in the wet forests, rivers, lakes, and swamps that covered much of the Carboniferous world. The rise of insects and other arthropods was one of the most important events in the long history of life on Earth. During the early history of the planet, almost all forms of life lived in the oceans. The land was empty except for bare rocks, sand, rivers, lakes, and areas shaped by wind and rain. Over a very long time, plants slowly spread across the land. As more plants became established, they changed the surface of the earth. They helped create soils, held moisture in the ground, and provided food and shelter. These changes made it possible for many kinds of animals to leave the water and begin living on land. Among the first and most successful of these animals were the arthropods. Arthropods are animals with hard outer coverings called exoskeletons. Their bodies are divided into different sections, and they have jointed legs that allow them to move in many ways. The group includes insects, spiders, scorpions, centipedes, millipedes, horseshoe crabs, and crustaceans such as crabs, shrimp, and lobsters. Although many arthropods still live in water today, many others became fully adapted to life on land. Their success came from a combination of useful features that helped them survive in changing environments. The ancestors of arthropods first appeared in the oceans hundreds of millions of years before insects evolved. Early marine arthropods were already among the most successful animals in ancient seas. They crawled along the sea floor, burrowed into soft mud, hunted smaller animals, or fed on dead organic material. Some grew to large sizes while others remained very small. They developed many different body shapes that suited different ways of life. Natural selection acted over countless generations, leading to a great variety of species. One important feature that helped arthropods succeed was their exoskeleton. This hard outer covering protected the body from injury and helped reduce water loss in species that later moved onto land. The exoskeleton also provided support for muscles, making movement more efficient. Since the exoskeleton could not grow with the animal, arthropods had to shed it from time to time in a process called molting. After shedding the old outer covering, a new and larger one formed. During this period, the animal was soft and more vulnerable until the new exoskeleton hardened. Jointed legs gave arthropods another great advantage. Their legs could bend at several points, allowing them to walk, climb, dig, swim, jump, or grasp objects. Different species gradually developed legs suited to their own lifestyles. Some had strong digging legs for moving through soil. Others had long walking legs for moving quickly across the ground. Some evolved special limbs for catching prey, cleaning their bodies, or carrying eggs. These many forms of movement allowed arthropods to spread into many different habitats. As plants spread across the land, they created entirely new food sources. Leaves, stems, roots, spores, seeds, and dead plant material became available for animals that could use them. Arthropods were among the first to take advantage of these resources. Some species fed directly on living plants, while others fed on dead leaves and wood that had fallen to the ground. By breaking down dead plant material, they helped return nutrients to the soil. This process supported the growth of new plants and helped maintain healthy ecosystems. The first arthropods to live permanently on land probably looked very different from most insects alive today. Many belong to groups that no longer exist or are represented only by distant relatives. These early land animals had to solve many problems. They needed to breathe air instead of extracting oxygen from water. They needed ways to avoid drying out. They also needed to reproduce successfully without depending entirely on water. Different groups of arthropods developed different solutions to these challenges. Some evolved breathing organs that allowed oxygen from the air to enter their bodies. Others developed body coverings that slowed water loss. Many learned to spend part of their lives in moist places, where drying out was less likely. Over many millions of years, these changes became more effective, allowing arthropods to live in forests, grasslands, deserts, mountains, caves, and many other environments. Among the earliest land arthropods were ancestors of modern millipedes and centipedes. Millipedes mainly fed on dead plant material, while centipedes became active hunters that fed on smaller animals. Both groups had long bodies with many segments and numerous legs. Their movement allowed them to travel across the forest floor, under fallen logs, and through leaf litter, where moisture remained high. Early spiders and their relatives also became important members of land ecosystems. They evolved special mouth parts for feeding on other animals and developed ways to capture prey. Some later evolved silk-producing organs that allowed them to spin webs, create shelters, protect eggs, or travel through the air on fine strands of silk. Silk became one of the most useful materials produced by any living animal. Scorpions were another important group of early land arthropods. Ancient scorpions first appeared in marine environments before some species adapted to life on land. They developed strong claws for catching prey and a tail ending in a stinger. Many early scorpions hunted insects and other small animals. Their basic body plan proved so successful that modern scorpions still closely resemble many of their ancient ancestors. The appearance of insects marked a major step in the history of life. Insects belong to the largest group of animals living today. Their ancestors evolved from earlier arthropods that gradually developed bodies divided into three main parts, consisting of the head, thorax, and abdomen. They also evolved three pairs of legs attached to the thorax. This body design became extremely successful and remains the basic structure of insects today. The head of an insect contains the brain, eyes, antennae, and mouth parts. The antennae help insects detect smells, touch, vibrations, humidity, temperature, and chemical signals. Different species have antennae of many shapes, depending on their needs. Some are long and thin, while others are short, feather-like, or club-shaped. The eyes of insects are also highly specialized. Many insects possess compound eyes made up of numerous small units. Each unit detects light from a slightly different direction. Together, these units allow insects to detect movement very quickly. Some insects also possess simple eyes that help measure light intensity. Good vision helps insects find food, avoid danger, and locate mates. The thorax is the center of movement. It holds the legs and, in winged insects, the wings. Strong muscles inside the thorax power walking, running, jumping, digging, and flying. Different insects have legs designed for different purposes. Grasshoppers have powerful, jumping legs. Praying mantises have grasping front legs for catching prey. Bees have legs adapted for collecting pollen. Water insects have legs shaped for swimming. The abdomen contains many internal organs involved in digestion, reproduction, and other body functions. Tiny openings along the sides of the body allow air to enter a system of tubes that carries oxygen directly to tissues. This breathing system works very efficiently for animals of small size. One reason insects became so successful was their small body size. Small animals need fewer resources than large ones. They can hide in tiny spaces, reproduce more quickly, and take advantage of many different food sources. Small size also allows large numbers of individuals to live in the same area without exhausting available resources as quickly. Another important reason for their success was their ability to reproduce rapidly. Many insects produce large numbers of eggs. Although many young insects die before reaching adulthood, enough survive to maintain healthy populations. Rapid reproduction also allows insects to adapt more quickly to changing environments because useful genetic changes spread through populations over many generations. The development of wings was one of the greatest achievements in insect evolution. Insects were the first animals to achieve powered flight. Before birds, bats, or flying reptiles existed, insects had already taken to the skies. Flight opened many new opportunities. Flying insects could escape predators more easily, travel greater distances, find new habitats, search for mates, and discover fresh food supplies. Scientists continue to study exactly how insect wings first evolved. Some evidence suggests that early wings may have developed from structures attached to the sides of the body that originally helped regulate temperature or allowed insects to glide. Over many generations, these structures became larger, stronger, and capable of powered flight. Muscles controlling the wings also became more advanced, allowing insects to fly with great skill. Early flying insects probably did not fly as well as many modern species. Over time, flight became more efficient. Different wing shapes evolved for different lifestyles. Some insects became fast flyers, capable of covering long distances. Others became highly skilled at hovering in one place. Some developed wings suited for short flights through dense vegetation. Dragonflies and their ancient relatives became some of the earliest successful flying predators. They possessed excellent eyesight, powerful jaws, and strong wings. They hunted other insects while flying and became important predators in ancient forests and wetlands. During parts of Earth's history, some dragonfly relatives reached wingspans much larger than those of living dragonflies. Their large size may have been supported by higher levels of oxygen in the atmosphere during that time. The atmosphere during parts of the Carboniferous Period contained much more oxygen than today. Higher oxygen levels made breathing easier for many arthropods because their breathing systems depend largely on the movement of oxygen through tiny tubes. Some scientists believe this allowed certain insects and other arthropods to reach unusually large sizes. Giant dragonfly relatives, enormous millipedes, and very large scorpions lived during these ancient times. The forests of the Carboniferous were filled with many kinds of arthropods. Thick vegetation created numerous hiding places and abundant food. Fallen leaves, dead wood, fungi, and living plants supported many plant-eating species. These animals in turn became food for hunters. Food chains became increasingly complex as more species evolved. Some insects fed by chewing leaves, stems, spores, or seeds. Others sucked fluids from plants using specially shaped mouthparts. Hunters developed sharp jaws or piercing mouthparts for capturing prey. Scavengers fed on dead plants and animals. Many species specialized in very narrow food sources, allowing many different insects to live together without competing for exactly the same resources. Different mouthparts allowed insects to exploit different foods. Beetles generally possess strong chewing mouthparts. Butterflies and moths evolved long feeding tubes for drinking liquid food. Mosquitoes developed piercing mouthparts for feeding on blood or plant juices, depending on the species. Flies display many different feeding methods, including sponging liquids and piercing tissues. The ability to change form during growth became another important reason for insect success. Many insects undergo metamorphosis. In complete metamorphosis, insects hatch from eggs into larvae that look very different from adults. The larvae feed and grow before changing into pupae. Inside the pupa, the body is reorganized into the adult form. Finally, the adult emerges ready to reproduce. Complete metamorphosis reduces competition between young and adults because they often eat different foods and live in different places. Caterpillars mainly feed on leaves, while adult butterflies feed mostly on flower nectar. Grubs may live underground feeding on roots, while adult beetles may feed above ground on leaves, flowers, or other insects. Some insects undergo incomplete metamorphosis. Their young, called nymphs, resemble small adults but lack fully developed wings and reproductive organs. As they grow, they molt several times until reaching adulthood. Grasshoppers, dragonflies, and true bugs follow this pattern. The rise of flowering plants much later in Earth's history created new opportunities for insects. Bees, butterflies, moths, flies, beetles, and many other insects became pollinators by carrying pollen between flowers. Both plants and insects benefited from this relationship. Plants achieved more successful reproduction, while insects gained food in the form of nectar and pollen. Not all insects interact peacefully with plants. Many species feed on leaves, roots, stems, seeds, flowers, or wood. Some create tunnels inside plant tissues. Others cause plants to produce unusual growths that shelter developing larvae. Plants responded by evolving chemical defenses, tough leaves, sharp structures, and other protective features. Insects then evolved ways to overcome many of these defenses. This ongoing process has continued for millions of years. Arthropods also formed close relationships with fungi. Many species feed directly on fungi, while others help spread fungal spores. Some ants even cultivate fungi as their primary food source. These farming behaviors developed much later, but demonstrate the remarkable complexity that insect societies eventually achieved. Social behavior evolved independently in several insect groups. Ants, termites, many bees, and some wasps live in highly organized colonies. Each colony may contain queens, workers, soldiers, and reproductive males. Different members perform different tasks, including caring for young, gathering food, defending the nest, cleaning tunnels, and building shelters. Communication became highly advanced in these social insects. Ants leave chemical trails that guide nestmates to food. Bees perform movements that help other bees locate flowering plants. Termites communicate using vibrations and chemical signals. These communication systems allow colonies to function efficiently. The construction abilities of arthropods are also remarkable. Spiders spin webs designed to capture prey. Termites build large mounds with complex systems of tunnels that help regulate airflow and temperature. Bees construct wax honeycombs made of many connected cells. Wasps create nests from chewed plant fibers mixed with saliva. Many arthropods developed defensive adaptations to survive attacks from predators. Some possess hard shells that protect soft body tissues. Others produce unpleasant chemicals that discourage attackers. Certain insects display warning colors that signal danger to predators. Some rely on camouflage that allows them to blend into leaves, bark, stones, or soil. Several insects mimic the appearance of other organisms. Harmless species sometimes resemble dangerous ones, reducing the chance of being attacked. Other insects resemble leaves, sticks, bark, bird droppings, or flowers so closely that predators often fail to notice them. Arthropods became important prey for many other animals. Early amphibians fed heavily on insects and other small arthropods. Later reptiles, birds, mammals, and countless other creatures also depended on them for food. Their enormous numbers helped support increasingly complex ecosystems. In freshwater habitats, insects also became highly successful. Mayflies, stoneflies, dragonflies, damselflies, caddisflies, and many flies spend much of their lives as aquatic young before emerging as flying adults. These insects connect aquatic and land ecosystems because nutrients move between the two environments during their life cycles. Marine arthropods continued to thrive as well. Crabs, shrimp, lobsters, barnacles, copepods, and many other crustaceans occupied countless ecological roles in oceans, rivers, lakes, and wetlands. Tiny crustaceans became important food for fish, whales, and many other aquatic animals. Spiders diversified into thousands of species, occupying forests, grasslands, deserts, caves, and human settlements. Different spiders developed different hunting methods. Some spin webs, while others actively chase prey. Some hide in burrows, waiting for passing animals. Jumping spiders rely on excellent eyesight and precise movements to capture insects. Scorpions adapted successfully to dry environments where few other arthropods could survive. Their bodies reduce water loss, allowing them to live in deserts and other harsh habitats. Most scorpions spend the daytime hidden under rocks or inside burrows before becoming active at night. Centipedes remained active predators throughout their evolutionary history. Their first pair of legs became modified into venom-injecting structures used to capture prey. Millipedes continued feeding mainly on dead plant material and played an important role in breaking down organic matter. Arthropods also became important engineers of the soil. Burrowing species mixed soil layers, improved air movement through the ground, and helped water enter more deeply. Their feeding activities broke down leaves, wood, animal remains, and waste. Microorganisms then completed the decomposition process, returning nutrients to the environment. Many insects survive seasonal changes through specialized life stages. Some spend winter as eggs, others as larvae, pupae, or adults. Certain species enter resting states during periods of cold, drought, or lack of food. These adaptations allow populations to survive difficult conditions until favorable environments return. Arthropods have developed many different reproductive strategies. Some lay eggs in soil, plant tissues, water, or protected nests. Others guard their eggs until they hatch. Certain spiders carry egg sacs attached to their bodies. Some scorpions give birth to live young instead of laying eggs. Many species provide little parental care, while others protect their offspring for extended periods. The senses of arthropods became increasingly advanced throughout evolution. Sensitive hairs detect movement and vibration. Antennae identify chemicals in the environment. Compound eyes detect rapid motion. Some insects hear sounds using organs located on their legs or abdomen. Others produce sounds by rubbing body parts together or vibrating special structures. Chemical communication became especially important. Pheromones allow insects to attract mates, mark trails, warn of danger, identify colony members, and coordinate many activities. These chemical signals are often highly specific, allowing members of one species to communicate without confusing other species. Many insects migrate over great distances. Some butterflies travel across entire regions during seasonal movements. Certain dragonflies complete long journeys between breeding and feeding areas. Locusts sometimes gather into enormous swarms that travel across wide landscapes in search of food. Disease has also influenced insect evolution. Many insects carry bacteria, fungi, viruses, and parasites. Some microorganisms harm insects, while others benefit them. Certain bacteria help insects digest food or produce essential nutrients. Other microorganisms protect insects against disease or predators. Some insects became parasites living on or inside other animals. Fleas feed on the blood of mammals and birds. Lice spend most of their lives attached to hosts. Parasitic wasps lay eggs inside other insects, where developing larvae consume the host from within. These relationships have shaped the evolution of both parasites and hosts. Human life today is closely connected with insects and other arthropods. Bees pollinate many crops. Silkworms produce silk used in textiles. Ladybirds help control agricultural pests. Dung beetles recycle animal waste. Countless insects decompose dead organic material and improve soil fertility. Some arthropods also create serious challenges for people. Locust swarms can destroy crops. Mosquitoes spread diseases such as malaria, dengue, yellow fever, and several viral infections. Ticks carry bacteria, viruses, and other disease-causing organisms. Certain beetles damage forests, while termites can destroy wooden buildings. Scientists continue studying arthropods because they represent the largest and most diverse group of animals on Earth. More than 1 million insect species have already been described, and many more remain undiscovered. New species are found every year in tropical forests, caves, mountains, deserts, freshwater habitats, and even cities. Many other arthropod groups also continue to reveal previously unknown species as exploration and scientific research expand. The long rise of insects and other arthropods took place over hundreds of millions of years through gradual evolutionary change. Small changes accumulated across countless generations, allowing different groups to occupy almost every environment where life can exist. Today, arthropods live in forests, deserts, grasslands, wetlands, rivers, lakes, caves, mountains, coastlines, polar regions, tropical regions, farmland, gardens, and human homes. They remain essential members of Earth's ecosystems through their roles as pollinators, decomposers, predators, prey, scavengers, herbivores, parasites, and soil builders, while continuing to display an extraordinary range of body forms, behaviors, life cycles, and ecological roles. The Carboniferous Period came to an end about 299 million years ago. It had lasted for many millions of years and was one of the most important periods in the history of life on Earth. During this long span of time, huge forests covered many parts of the land. Thick layers of plant material slowly turned into coal. Insects became more diverse, amphibians spread into many environments, and the earliest reptiles appeared and slowly increased in number. By the closing part of the Carboniferous, however, Earth was changing in many different ways. The climate, the land, the oceans, and the living things were all affected by these changes. The world that existed at the beginning of the Carboniferous was not the same world that existed at its end. These gradual changes prepared the planet for the beginning of the Permian period. The end of the Carboniferous was not marked by a single event that suddenly changed the entire planet. Instead, the transition happened over a long stretch of geological time. Rocks that formed during the latest Carboniferous and the earliest Permian often show that many changes took place little by little. Scientists study these rocks, fossils, and ancient sediments to understand how the environment changed and how living things responded. The evidence preserved in these rocks provides a detailed record of shifting climates, changing coastlines, mountain building, and the movement of continents. One of the most important changes during the closing part of the Carboniferous involved the arrangement of Earth's continents. Throughout much of the Carboniferous, many landmasses continued moving toward one another because of the slow movement of tectonic plates. These slow movements caused continents to collide, join together, and create larger land areas. By the end of the Carboniferous, most of Earth's major landmasses had become connected into the giant supercontinent known as Pangaea. This enormous landmass stretched across a large part of the planet and greatly influenced weather patterns, rainfall, temperatures, and the movement of air. The formation of Pangaea affected many parts of the environment. Large inland regions became farther away from the oceans. Areas located deep inside the supercontinent often received less moisture because ocean winds had to travel much greater distances before reaching them. As a result, many inland regions slowly became drier. Rainfall decreased in many places, and the thick, wet forests that had covered vast lowlands during much of the Carboniferous began to shrink in several regions. The great coal swamps that had become common during earlier parts of the Carboniferous depended on warm temperatures, abundant rainfall, and constantly wet ground. Water covered many low-lying areas, allowing dead plant material to build up faster than it could fully decay. Over long periods, these thick layers of plant remains became buried beneath sediments and later formed coal. As climates became drier in many places toward the end of the Carboniferous, conditions became less suitable for maintaining these enormous wetlands. Water levels often dropped, wetlands became smaller, and many swamp forests gradually disappeared. The reduction of these swamp forests had important effects on plant life. Many plants that had flourished under constantly wet conditions found it harder to survive as rainfall patterns changed. Giant club mosses, large horsetails, and many tree ferns became less common in areas where the land became dry. Some continued living in places where moisture remained plentiful, while others experienced a steady decline over long periods. At the same time, plants that could better tolerate drier conditions became more successful. Seed plants increased in importance because seeds offered better protection for young plants than spores alone. Seeds contained stored food and protective coverings that helped developing plants survive periods when conditions were less favorable. This adaptation allowed many seed-bearing plants to spread into environments where constant moisture was no longer available. Among these seed plants, early gymnosperms became increasingly important. Their ability to reproduce without depending entirely on standing water gave them an advantage in many regions. Pollen carried the male reproductive cells through the air, reducing the need for water during reproduction. This feature became especially valuable as many landscapes became drier near the end of the Carboniferous. The changing climate influenced soils as well. In wetter environments, soils remained saturated for long periods. Organic material accumulated because it decomposed slowly under waterlogged conditions. As many regions dried, soils experienced different patterns of weathering and erosion. Rivers carried sediments into lakes and shallow seas, creating new layers of sandstone, shale, and other sedimentary rocks that today provide valuable evidence about these ancient environments. Mountain building also continued during the closing stages of the Carboniferous. As continents collided, enormous forces pushed rocks upward, creating extensive mountain ranges. These mountains influenced rainfall by changing the movement of air across the land. They also supplied large amounts of sediment as rain, rivers, wind, and ice slowly wore away their slopes. These sediments spread across nearby plains and coastal regions, becoming part of the geological record that scientists study today. Many of the mountain ranges formed during this time were connected with the collisions that helped create Pangaea. Although these mountains have been worn down greatly through millions of years of erosion, their ancient roots remain preserved in many parts of the world. Rocks within these regions contain valuable information about the powerful tectonic forces that shaped Earth's surface during the late Carboniferous. The oceans also changed as the Carboniferous drew to a close. Changes in sea level affected the extent of shallow seas that had covered parts of many continents earlier in the period. In some places, sea levels fell because large amounts of water became locked inside expanding glaciers. In other places, movements of the Earth's crust caused local rises or falls in sea level. These changes repeatedly exposed and flooded coastal plains, creating alternating layers of marine and land sediments. Evidence from sedimentary rocks shows that sea levels rose and fell many times during the late Carboniferous. These repeated changes influenced the distribution of marine habitats. Organisms living in shallow coastal waters had to adapt as shorelines shifted over long periods. Some marine communities expanded into newly flooded areas, while others disappeared from regions where the sea retreated. Glaciers played a major role in shaping the climate during the end of the Carboniferous. Large ice sheets covered extensive parts of the southern regions of the supercontinent, especially areas that now form parts of South America, Africa, Antarctica, Australia, and the Indian subcontinent. These glaciers expanded and contracted several times as temperatures changed. Their movement carved the landscape, transported rocks over long distances, and left behind sediments that remain visible in the geological record today. The presence of these glaciers shows that Earth experienced significant cooling during parts of the late Carboniferous. This cooling influenced global weather patterns and contributed to changes in sea level. When glaciers expanded, more water remained frozen on land, causing sea levels to fall. When glaciers melted, water returned to the oceans, raising sea levels again. These natural cycles affected coastlines across much of the world. Scientists have identified glacial deposits from this time by studying distinctive rock formations. These include sediments left directly by moving ice, as well as scratches and grooves carved into bedrock beneath glaciers. Such evidence helps reconstruct the ancient climate and confirms that large areas experienced prolonged cold conditions during the closing stages of the Carboniferous. Not every region became cold or dry at the same time. Earth's climate remained varied across different parts of the planet. Areas near the equator often continued experiencing warm temperatures, although rainfall patterns gradually shifted. Regions closer to the poles remained much colder because of the extensive glaciers covering large areas of land. The development of the amniotic egg represented one of the most important biological advances during this time. This type of egg contained protective membranes and a shell that helped the developing embryo remain moist while growing on land. Because of this adaptation, early reptiles no longer needed to return to ponds or swamps to reproduce. They could spread into many environments that amphibians found more difficult to occupy. As reptiles expanded into new habitats, they gradually diversified into different forms. Some remained small insect eaters, while others adapted to feeding on plants or other animals. These early reptile groups laid the foundation for the many reptilian lineages that became increasingly important during the Permian period. Insects also continued evolving during the end of the Carboniferous. Earlier in the period, high oxygen levels had supported some very large insects and other arthropods. Toward the close of the Carboniferous, atmospheric conditions slowly changed. Oxygen levels gradually declined from their earlier peak, although they remained higher than modern levels for some time. These changes influenced the sizes and distributions of many insect groups.